Okay, so now I will be explaining question 10. So the important concept in question 10 is conservation of energy. So their energy exists in two forms, two general forms, and that's kinetic energy, which I will abbreviate as KE, and potential energy, which I'll abbreviate as PE. And kinetic energy is basically the energy of motion. When something is in motion, it has energy, and it is given by the equation 1/2 mass times velocity squared. Okay, so the other type is potential energy, and the form I am showing it in today is gravitational potential energy, and it has the equation mass times gravity times the height which it is from. So basically, potential energy is energy that matter gains from its arrangement or position, and it basically has the potential to do work. So that's kinetic and potential energy. So conservation of energy. So energy in the universe, energy stays the same and is conserved. But if we're talking about isolated or non-isolated systems, just looking at a specific system, energy can be conserved in that system, or it is conserved in that system if it's isolated, and it's not conserved if it's non-isolated. And it can be, in a non-isolated system, it can be lost to heat, friction, other examples. But for this question, we are dealing with an isolated system, so the initial energy is equal to the final energy. So this is going to be, the conservation of energy is going to be an important topic in this question. Okay, so now I'm going to explain or read the question out loud. So there's a basic overview for the question and then the more specific question. So particle A and particle B, each of mass m, move along the x-axis, exerting a force on each other. Okay, so I'm just going to draw that picture just to make it clear. So this is particle B, and this is particle A. Move along the x-axis, each exerting a force on each other. Okay, the potential energy of the system of two particles associated with the force is given by the equation U, which is potential energy, is equal to beta over r squared, where r is the distance between the two particles, so here, and beta is a positive constant. At time equals 0, particle A is located at x equals 2d with an initial speed of v to the left. Okay, so this is at x equals 0, and this is located at x equals 2d away, so that's the r that we're dealing with. And it's moving an initial speed of velocity initial to the left, and particle B is at rest at the origin as shown in the figure above. Okay, so that's the situation we're dealing with in this problem. Question 10 specifically, which of the following equations could be used to find r min, the minimum distance between the masses as particle A approaches particle B? Okay, so basically in this question, to figure it out, we need to set up the conservation of energy equation, because that would allow us to put the initial and final kinetic energies, the initial and final potential energies, and we would have enough variables, or we would be able to eliminate variables and find our min. So what I'm going to do is, in this situation, since, as I said before, it's an isolated system, no energy is being lost or gained in the environment. So I'm just going to put here, initial energy is equal to the final energy of the system. Okay, so first I'm just going to deal with the initial energy, just to explain what the initial energy is in this system. So E initial is going to be equal to the initial potential energy plus the, here, I'll write potential energy plus the initial kinetic energy, because kinetic plus potential is the total energy. Okay, so for the initial potential energy, in the equation or in the question, they say that the initial potential energy, or the potential energy in this situation, is beta over r squared. Now, they say in the problem that A is located 2D away from B. So we know that r is going to be 2D. So we can put that there. U is equal to beta over 2D squared. And so then we're going to get the initial potential energy. So here I'll put an I there to show initial, is going to be equal to beta over 4D squared. So I'm just going to circle that and remember it when we plug everything in. Okay, so now I need to find the initial kinetic energy. So remember at the start, particle A is moving towards particle B. So only particle A will have kinetic energy. So it's just going to be 1/2 mv initial squared. So that's because kinetic energy is the energy of movement, and that's the only thing that's moving at the beginning. So I'm going to circle this, the initial kinetic energy. Now we're going to go on to the final energy. So the final potential energy of the system, as it says in the equation, as it's approaching it, we're going to get the beta over, and then it says here in the question, could be used to find r min, the minimum distance between the masses as particle A approaches particle B. So the radius is going to be r min squared. And so I'm just going to circle that, and remember this is what we are solving for. Okay, so now I'm going to find the final kinetic energy. Okay, so remember at the end, both particle A hits particle B, so they're both moving at the same time. And then since it hit it, they're going to each have half the amount of velocity. So it's going to be 1/2 m, and then the initial velocity that particle A hits particle B squared plus 1/2 m v initial squared. This is for particle A and particle B. Okay, so we have this. Oh, and then we can simplify this to m over 4. So this is our more simplified version of kinetic energy at the end. Okay, so now that we have all of this, we can plug it in with the initial energy is equal to the final energy. Okay, so we get initial potential energy, beta over 4d squared plus 1/2 mv squared initial kinetic energy equals beta over r squared min plus m, and then we have v squared over 4. Okay, so this answer will lead to the correct answer. This can be simplified to m over v naught over 2 squared. So the correct answer will be B because that's what it matches. So this is, we figured out from the conservation of energy, and we got the correct answer is B.